So in the last video, I introduced this thing called the law of sines, which is this equation right here, which is a very good one to have memorized. And what it does is it relates together angle measures and side lengths in arbitrary triangles, triangles that are not right triangles, like you see pictured here. So for example, suppose you had this triangle and you know that this is 60 degrees down here and this is 45 degrees up here, and I'm calling this side length B and this side length C and this side length A, and we know A equals 3, but we don't know B or C. And suppose we want to find everything we don't know, namely side lengths B and C and angle C. Turns out you can do all of that using the law of sines. Note that what we have in this case are two angles and one side. That's one of the two applications of the law of sines. In the next video, I'll talk about how you can also use the law of sines if you just have one angle, but you have two sides. But first, two angles and a side. And note that in this case, things are labeled. I'm calling this little a, so therefore capital A must be equal to 60 degrees because capital A is always across from little a. And since I'm calling this little b, capital B must be equal to 45 degrees here, again, because the angle is opposite the side length. So the first comment that I want to make is if you have two angles in any triangle, you really have all three. There's this fact that the sum of the interior angles in a triangle always equals 180 degrees. So if you know capital A and capital B, you really know A, B, and C. These three things have to add up to 180 degrees. If I add these two together, I get 105 degrees. So I need 75 degrees more. Capital C must be 75 degrees, even if that's not given. So all the examples on this page where I say you have two angles, I don't know, maybe there's a little asterisk there, which says really three angles. At any rate, that's the kind of low-hanging fruit. We still have to figure out little b and little c. How can we do that? Well, let's start with little b. I know little a here, and I want to know little b, so it's going to make sense to use the first equality here in my law of sines. I know this is kind of weird having two different equal signs, but don't let that throw you off. It's just saying that this thing is the same as this thing, and this thing is also the same as this thing, and this thing is the same as this thing. So I can kind of choose any two that I want and set them equal to each other based on the information that I have. If I know little a and I want to know little b, I'm going to take the first two of these guys and I'm going to say the sine of capital A over little a must be the same as the sine of capital B over little b, and then I'm going to plug in the information that I have. Capital A is 60 degrees, so the sine of 60 degrees divided by whatever little a is, 3 in this case, must be the same as the sine of B. B is 45 degrees, divided by little b, which is the thing that I don't yet know. The nice thing about this is there's only one unknown in here, little b, so it's easy enough to solve for it. It's a matter of preference whether you want to evaluate sine of 45 and sine of 60 at this stage or wait to do it. I usually wait to do it. I get the b by itself first, and then I figure out what those things are equal to. So I'd multiply the b up to the top over here, multiply the 3 up to the top over here, and then divide the sine of 60 over here to get b is equal to 3 times the sine of 45 degrees divided by the sine of 60 degrees. And only then, after I've isolated b, do I plug in what the sine of 45 degrees and the sine of 60 degrees are equal to. But again, that's just personal preference. You do what you want. The sine of 45 degrees off your unit circle is the square root of 2 over 2. The sine of 60 degrees off your unit circle is the square root of 3 over 2. So I have a fraction over a fraction. Maybe it's easier to see it if I write it as 3 root 2 over 2 divided by the square root of 3 over 2. I take the fraction on the bottom and I flip it upside down. That changes the division of fractions into multiplication of fractions, which is nice. These 2's cancel out. I get 3 root 2 over the square root of 3, which is pretty close to a fine answer, but I guess technically we should rationalize the denominator. So let's multiply the top and the bottom by the square root of 3, and I get 3 times the square root of 6 divided by 3, because root 2 times root 3 is root 6, and root 3 times root 3 is 3. And then this 3 and this 3 can cancel out, and I get the square root of 6 as my answer for what b is equal to. We've now done 2 of the 3 parts, right? We were asked to find B, C, and capital C. Capital C was easy. B we found using the law of sines. What about little c? Well, we can just use the law of sines again. Now I know little a and little b, and I want to know little c. So I can either say sine of a over a equals sine of c over c, or sine of b over b equals sine of c over c. It really doesn't matter because I know both a and b, and I want to know c. Suppose that I chose this one, sine of a over a equals sine of c over c. The reason I chose that is because a is a nicer number, it's just equal to 3, whereas b is the square root of 6. So instead of involving another square root, which is what would happen if I set the sine of b over b equal to the sine of c over c, I'll avoid that by taking these two and setting them equal. At any rate, now I'm just plugging in numbers. The sine of 60 degrees, which is a, divided by little a, which was given to be equal to 3, is equal to the sine of c. C is 75 degrees. Divided by little c, that's the thing that I don't know. To solve for little c, I'm in a situation a lot like I was in over here, where I have a bunch of numbers and one letter. Let's solve for that letter. Get the c all by itself. I'll multiply the c up to the top over here, the 3 up to the top over here, and divide by sine of 60, and I'll get c is equal to 3 times the sine of 75 degrees divided by the sine of 60 degrees. And you're like, wait, there's a problem. I know the sine of 60 degrees, that's root 3 over 2. I don't know the sine of 75 degrees. Well, I think you actually do know the sine of 75 degrees, but here is where this gets a little bit tricky. This is the right answer the way it's written right now. You could argue that it's an unsimplified version of the right answer, but it is the right answer. I mean, this is just some number. It's an expression that represents the length of this side C. Do I, the student, have to go any further? Well, it depends. Are you being asked to simplify your answer? I'll always be really explicit about this and let you know whether this is sufficient or whether you have to go further. I think on the homework, typically this right here will be sufficient. You can type in expressions. But on a quiz, I might tell you, simplify your answer completely so that it doesn't involve any trig functions. In other words, figure out the sine of 75 degrees and the sine of 60 degrees. The sine of 75 degrees, one way I could get there is with angle addition. I could say that that's the sine of 30 degrees plus 45 degrees. And then if you go back to 7.2 and 7.3, we learn that the sine of a plus b is sine of a cosine of b plus cosine of a sine of b. Again, you don't have to have that memorized. So using that formula, this would be the sine of 30 degrees times the cosine of 45 degrees plus the cosine of 30 degrees times the sine of 45 degrees. I evaluate all these off my unit circle. The sine of 30 is a half. The cosine of 45 is root 2 over 2. The cosine of 30 is root 3 over 2. And the sine of 45 is root 2 over 2. Now I multiply stuff together. I get root 2 over 4 plus root 6 over 4. So I get the square root of 2 plus the square root of 6 divided by 4. So that's my answer. No, that's just the sine of 75 degrees. What I'm trying to figure out is little c here. Little c is equal to 3 times the sine of 75 degrees divided by the sine of 60 degrees. The sine of 60 degrees is root 3 over 2, and the sine of 75 degrees, as I just figured out down here in red, is square root of 2 plus square root of 6 divided by 4. Make it a fraction divided by a fraction so we can simplify this mess. I can multiply the 3 up top and get 3 root 2 plus 3 root 6 divided by 4 divided by the square root of 3 over 2. And then I could flip things upside down to change the division of fractions into the multiplication of fractions. So let's see, this 4 and this 2, I can cancel some stuff out. And now this is gone and this is a 2, so I get 2 root 3 in the denominator, which is a pretty good answer, but I guess we should rationalize the denominator, multiply the top and the bottom by the square root of 3. The square root of 3 times this term gives me 3 times the square root of 6, because root 2 times root 3 is root 6. For this second term, I get 3 times the square root of 6 times 3, which is 18. And then down in the bottom here, I have 2 times the square root of 3 times the square root of 3, so I get 2 times 3, or 6. At this stage, you could call it good, or you could cancel out these 3's with this 6 and call it the square root of 6 plus the square root of 18 divided by 2. And as long as we've gone this far, you might recognize that each of these terms have a square root of 2 in them. And if you pull out that square root of 2, you're left with the square root of 3 from here and a square root of 9 from here. But the square root of 9 is just the number 3. So another way you could write your final answer is like this. I don't need you to go any further than this. And frankly, if you got this far, I'd be pretty happy. And if it didn't say to rationalize the denominator, you get full credit for that as well. The big takeaway here is just that if you have a triangle and you have 2 angles, you really have 3 angles. And if you have all 3 angles in one side, you can solve for the remaining sides. And sometimes that won't be too bad. You can just use memorized values off your unit circle. And sometimes that can be harder if it references an angle that you don't immediately know the sign of. And yeah, there's solutions. There's ways you can get around that. For example, sometimes you can use angle addition if this angle is really lucky. But angle addition formulas wasn't really part of the chapter 8 stuff. I'm just trying to show you how old stuff can tie into the new stuff. If you can get to the point where given this triangle, you can find capital C, and given this triangle, you can find little b, and you can come up with an expression for little c, so something that looks like this, we're good. That's all the new information out of this section. The rest of it was just reminding you of stuff that maybe you already knew. One last comment before I end this video. This time I told you this is little a, this is little b, this is little c. I named all these things for you. They might not be named for you. That's fine. If they're ever not named for you, just name them yourself. Just be careful about the way you name them. If you call this little c, you have to call this capital C. If you call this little a, you have to call this capital A. Capital letters have to be across from the lowercase version of that same letter. Often things will be labeled, but not always. You'll see some in the homework where they're just like, this side length is 3, and they don't name it at all. What is this missing side length over here or something, and you have to solve for it. Just make sure you're comfortable putting the letters in and using this formula, and you should be good.